Okay, so let's talk about two examples. And I'm going to try very hard in these examples to kind of review and use all the different ways that we've learned in this lesson to graph functions. So sketch the graph of this function. Great. So the first thing I'm going to do is realize that if I say z equals f of xy equals 6 minus 3x minus 2y, well, if I rearrange everything and put all the variables on one side, that's what this looks like. This should look familiar because this is the equation of a plane with normal vector 3, 2, 1. And to find a point on the plane, we could set x equal to 0, y equal to 0, and then z would be equal to 6. So using this, I could actually, plot the plane. I could use technology to help me do that, or some of the techniques that we talked about in our plane lesson earlier. I'm actually just going to give you the picture here so we have it. And I'm going to generate that picture using a second graphing technique. So I'm going to say, what if x is 0? Well, if x is 0 up here, then I just get z equals 6 minus 2y. So I can then go over here and graph that. So in the yz plane, I would start at 6 and I would have a slope of negative 2. So I would end up here at y equals 3. What if y equals 0? Well, if y equals 0, then I have z equals 6 minus 3x. So in the xz plane, I would again start at 6, and then I would have a more negative slope, so I would end up a little faster to the axis at x equals 2. And then if z equals 0, what happens there? Well, then if I set z equals 0 up here, I get 3x plus 2y equals 0. I get y equals minus 3/2 x. So that's this line here. So this is the region of the plane in the first octant. And, that tells us that the plane, the full plane, does something like this. It kind of slices the xy plane here, and then it keeps going that way. So again, this is a second way that you can try to graph a multivariable function. You can look at the curves or lines that are generated when you set x, y, and z to be 0. Okay, I'm going to keep the picture, but I'm going to change here the way we graph it. Now I'm going to look at the level curve view of graphing this. So if z is 6 minus 3x minus 2y, what if I set it equal to a constant? I'm going to rearrange things here. I get 3x plus 2y equals 6 minus c. And this starts looking like a line, so I'm going to say y equals 6 minus c over 2 minus 3x over 2. And then I can start generating contour plots. So, for example, if c is 6, then this would be 0, and I just get the line minus 3x over 2. If c is 8, then this would be 6 minus 8, that's negative 2, divided by 2, negative 1, minus 3x over 2. And we'll do it one more. If c is 4, this would be 6 minus 4, which is 2, divided by 2 is 1, minus 3x over 2. Great, so then how would I plot this? Well, if I'm thinking about a contour plot, I'm going to erase this and move over my plane. If I'm thinking about a contour plot, then I'm going to graph x and y axes here. If I graph this one, it's just a line that slopes down. I'm going to label this c equals 6. If I graph this one, it's a line that is 1 unit below that one. So this is c equals 8. Then if I graph this one, it's a line that's 1 unit above the first one. So that's c equals 4. And again, it will take some time. I don't expect you to be able to do this anytime soon. It takes some time to be able to see this two-dimensional plot and visualize the 3D surface. It'll take some time. But you'll notice here that if we go that way, the z values are going up. Remember, z equals c for the contour plots. So what we're getting is then we're getting lines that are going higher and higher, coming out of your screen. And you can see that that's exactly what we would get if we looked at the plane from this point of view. So I'm going to end this example by going back to the plot here and then turning certain things off. So here's the plane down here, and then I'm going to just look at the plane first. So there's the plane, right? Indeed, it slants from the z-axis down and cuts the x and y-axis. You can see over here it cuts it at 2, and over there it cuts it a little bit more at 3. And then I'm going to go over here then and generate the contour plot so we can see those lines. So there's the contour plots. Create the plots, and there are those lines. So we see here, oops, it likes to do that to me. So I will try one more time before we get to the full, before we get to the full graph. Generate the contour plot down here. Let's see. Create the plots. Great. Okay, I guess if I click there, so I know what I'll do. I'll be creative. Create the plot. Great. If I do this, then the iPad doesn't register my click if I drag my finger. So that's a trade secret. So here we are looking at all the contour plots, and here's exactly what we had seen. If c equals 6, then you get -3/2. And then if c equals 8, it's 1 unit lower. Here's -1. And then if c equals 4, it's 1 unit higher. There we go. So this is the plot that we see that as the z-values increase, then the lines are moving this way. Notice that unlike the other plot that we had seen, the paraboloid, the distance between these contours is exactly the same. So that's telling us the linearity of the plane, basically. The change in z from 0 to 1 is 1 unit, from 1 to 2 is 1 unit. All the change in z's here are 1 unit. That's how we created the contour plot. But the x and y values that live on those planes, z equals 0, z equals 1, that cut the graph, they're not getting any closer, they're not getting any further apart. So in some sense, you know, there's linearity as we move up the surface. And then certainly, right, when I take my finger away and do that, that's exactly what happens. That is the linearity that we see as we move up the surface. Even though the z-values are increasing, they're increasing at the same rate. Again, there's a word that foreshadows derivatives. Okay, great. So everything we have said makes sense so far. So let's go ahead and move on to the last example in this lesson. We'll do something similar here. So we're going to add a few things. So consider this function, find the domain, find the range. So in terms of the domain, well, it sometimes pays to think a little bit about what the function is doing. Here we're taking an x and y value, there they are, subtracting it from 4, okay, but then we're taking the square root. So at least in this class, we can't take square roots of negative numbers. So we need this argument of the square root to be non-negative. So that tells us that x squared plus y squared is less than or equal to 4. And that plot in the xy plane is a circle or disk of radius 2. So this is the domain D, a disk that includes the boundary x squared plus y squared equals 4. So that's our domain D. If I then go to find the range, well, I need to think about the set of possible outputs. Okay, so if I start thinking three-dimensionally here, the set of possible outputs, I don't have to do this, but to tie things together, if I go off and plot my domain here, that's my domain in the plane. And then if I pick, for example, a point like 0, 0, and I put it into this function, I get square root of 4, which is 2. So that's up here. If I pick any other points in this domain, I am going to end up, because this is 4 minus x squared plus y squared, I'm going to end up with a positive number that subtracts from 4. And then I will take the square root. So the answer will be less than square root of 4, less than 2. In other words, I'll be down here somewhere in some lower part of the z-axis. All of this is to convince you that the z-values, the maximum they could be is 2. and everything else, all other xy points in the domain, map to a z-value that is less than 2. Okay, and then how low can we go? Well, it is a positive square root, so I can't get a negative number. No matter what x and y value I put in, I can't get -4, for example. So the lowest that I can go is z equals 0. So that helps me figure out my range. So the range is z between 0 and 2. So that's the interval 0 to 2. So that's my range. Great. So then now let's try to sketch, number 2, the graph of the function. I have started doing that, but this is the plot points version, which, as we said earlier, takes way too long. We could do the x equals 0, the y equals 0 versions, right? But instead, I'm going to choose to do the contour version. So if I set the function equal to c and start looking at its contours, what do I get? If I rearrange things, I get 4 minus c squared. So the contour plots are again circles of varying radii, except that they don't go on forever, like in the paraboloid case, because the largest that c can be is c equals 2, right? We said that. Remember, c is the z value, and the largest z is 2. And then, so the smallest that c can be is 0. So the largest circle that I will get in this contour plot is when c is 0. I get the circle x squared plus y squared equals 4. So this is, let's just call this c equals 0. And let's say that this is 2. And the smallest circle I get is when c equals 2. When c equals 2, this whole thing is 0. And I'm back to x squared plus y squared equals 0, whose only solution is the point. So what we see going on here, if I remove some of the clutter, for example, I could choose a different c value, like, I don't know, c equals the square root of 3. And if I do that, over here, this would become 4 minus 3 is 1. So I get the unit circle. So the unit circle is over here, and this is c equals square root of 3. So the picture we get emerging from this contour plot is that the surface starts off in the xy plane looking like a circle of radius 2. And then as c increases to square root of 3, as the z value gets higher, the surface shrinks a little bit in the sense of on the plane z equals square root of 3, the x and y values for the function are the unit circle. So going over here, right? If I remove some of this z-axis clutter, just redraw it. If I remove some of the z-axis clutter, then I can redraw my function in 3 space based on what the contour plot is telling me. So here's x, y, z. So here is my original z equals 0 contour that is on the function. And then if I go up to square root of 3, I have this contour down here, a smaller size circle. And then over here, this point, if you remember, was when c was square root of, was when c equals 2. So that is even higher up here, z equals 2. I have a point. So you might get a sense of what's going on here. We are talking about a hemisphere. I have certainly not successfully drawn it as a hemisphere, but that's exactly what it is. So I actually ended up doing number 3, also a version of that, sketching the level curves for the function. So to finish up, let me then show you the hemisphere that we have drawn. So I put that in here so that we can see. That's the first graph here. One quick thing to mention, notice that, there are these weird lines, right? At a certain point, computers, applets have trouble evaluating square roots of really small numbers and taking natural logs of really small numbers and all these transcendental functions of small numbers. So these are artifacts. These long lines are actually not part of the graph. The graph of the surface really is this hemisphere. So I'm going to pan around so you can see it is really a hemisphere. And the extent is exactly what we thought from the domain is exactly what we thought, which is the set, here you can see it, in the xy space, is the set of the unit circle with radius 2, and it's the disk. So going back to this view of things, let's see if that is possible. Maybe it's not. Okay, well, sort of. I don't know where this... Oh, this is the old contour plot. So let's create the new contour plot. There we go. I am going to change the step size here for this contour plot. So let's put it at, I don't know, 0.5. So we get a few more contours that we can look at. Create the plots. There we go. Great. So now we can look at the contours. And you can see again that the contours up here or over here are closer to each other than these two are to each other. So unlike the plane example, this is another kind of surface where even though we're changing by the same z value every time, we're going from 0.5 to 1 to 1.5 and then to 2. Here's 2, if you can see it really tiny there. We're going up, or we're changing by 0.5 in z every time. The contours sometimes are close together, sometimes are further apart. So again, wherever the contours are close together, the function is changing rapidly. Wherever the contours are far apart, the function is changing less rapidly. So if we click here and take a look at the surface, you can see that pretty clearly. Down here, right, this contour and that contour, there's a lot of curvature here. The function is changing quickly. Up here between this contour and the top, it's a much gentler curvature. So the function is not changing as quickly. So that makes sense. So beyond that, I encourage you, as usual, to go to this site. There's all sorts of things that you can try. You can experiment with putting in different functions. If you hit select and a function, sometimes functions just pop up. So let's look at this one that popped up. Here is, in other words, there are some pre-defined functions. So this is a very crazy looking function, but if you wanted to, you could generate a contour plot for this function and then try to get a sense of what's going on here. So you can certainly do that.